I would like to do is, if you guys could get kind of where we can look towards the front, and I guess you'll be looking all around here. I'm going to have you look. So much junk up here. All right. So you're recording your answers. 3 pretty big ideas about sound in these different columns. Now, the questions that went with them related to how things make sound, how sound travels, and then how sound has different qualities. Okay? The ideas that I wanted to kind of summarize over here, pretty similar. How do things make sound? How does the sound travel through air? And then how do we hear sound? So why don't we start with just the big thing we've been talking about to start with was just how do things make sound. We looked at the bass, we looked at the drum, and we also used tuning forks, right? So, drum, and then the tuning fork. How are they actually making that noise, or how are they making that sound? General thoughts? How about this? What do they all have in common? You hit a drum, you hit a tuning fork, and you pluck a string. What you say? Vibration. Vibration? Brian, do you agree? Jose, were you going to say the same thing? Yeah. Okay, vibrations, right? What are those all vibrating against?
Air.
Air, yeah. So, yeah, sorry, it should call on you, your hand up. But yeah, air. So, if we have this, let me see which one I want to use. Okay, I want to use this one, and I want to use this one. Alright. So, let's listen to this, and I want you to compare these two, okay? So, this one. Actually, before we compare, why don't you think about, what do you think the air is doing around this fork, right? It's immersed in air, right? We're surrounded by air. What do you think that air is doing right next to it? The little invisible particles of air. The fork's vibrating, right? And they're being pushed away. Yeah, and then when the fork flexes back in, they kind of spring back. Now, there was a diagram in your reading that looks kind of like this. You ring this fork, right? And when you looked at that one that was longer, you could see the fork vibrating out and in, out and in. These little dots there represent the air particles, and as the fork hits them, they kind of press them together, and then as it springs back, they kind of are able to spread out a little bit. Now that movement of the fork, that's creating a sound wave that allows that energy to travel from this fork from one particle to another, and that's what we keep talking about as a sound wave. Now it's kind of hard to see there in those dots because it's just, what, this far away from the fork. So look at this one. This is a model of, this is an actual photo or anything. It's made by a computer, but I'm going to turn this off for just a second. Take a look at that. Those are air particles that are the little dots. And can you see how that one particle pushing into another, then bumps into another, then bumps into another? And that's what the wave is that kind of disturbance or bumping into one another that travels away from the moving fork. Now when we move the slinky back and forth, there's a few ways we can move the slinky. If we wanted to simulate what happens actually with sound and the energy in a sound wave, it thinks that they could show that motion with a slinky. Okay? Luis, I know that you and I talked about this a minute ago. Would you be willing to help me? Okay, come here. You don't, this is, I know this is like a big thing to have to do, but come over here in the center. And I think, will this be a place, I think if you guys just turn to look here so we can see the, we'll use this to simulate what's happening with the wave through the air. And we'll put this down here. So if Luis is going to simulate a sound wave traveling through the air, what would you tell Luis to do if you wanted to be accurate and tell him how sound really looks like moving through the air? Jordan?
You have to like quickly compress the air, like push it forward so it moves all the way down the slinky.
Those directions you could follow? All right. Is that sort of like you're talking? Okay. Now, do you see how he's moving that forward and back?
Yeah.
See, there's a small kind of like compression that travels all the way down the slinky. Now, do it one time real hard. Okay. See how when he does it a little harder, what do you notice happening with this the slinky? Yeah.
Easier to see them. Like it's easier to see it moving closer together and spreading back apart.
Would you guys agree it's easier to see? Like if I go like this, you can see that going down. Why is it easier to see? What are you thinking?
Because it's more dense, like the harder you push, the more it bunches together.
Yeah, that compression there, that's a great description. It's more dense there, and you can see it a little bit better. Now, when Luis went from this to pushing it hard, what would that have sounded like if you were to actually hear sound doing that? What would have changed with the sound? Would it have been, yeah, Latrell?
Louder, I guess.
What do you guys think? Louder? Or what's the other option?
More intense, yeah.
Okay, so the two things that we heard changing with the tuning forks was pitch, like how high or low, or if you hit it real hard, the volume changes, right? Or the loudness. What do you think would be more likely the thing if Luis is just pushing on this harder? Volume, do you think, or the high or low tone?
Higher, lower tone.
Okay.
I mean the volume.
Well, let's do this. Thanks. I want to show you something real quick with the tuning forks, okay? So we had two of them, right? We had the long one here, and the short one. You guys remember the difference when you tried these?
Mm-hmm.
If somebody remembers, just say it. How about this one?
Lower pitch, higher
Smaller
pitch,
one was
higher
higher.
pitch.
Larger one was lower pitch, so let's just hear that. Does that seem to fit? Higher pitch, lower pitch? Okay. Now, do you remember whenever we touched them to paper, you could hear them vibrate? Let's compare how fast they're vibrating. Okay. Now let's hear this one. Okay, which sounded like it was vibrating faster? The first one or the second one?
Second one.
This one, right? It was like... That sounds like a mosquito buzzing versus, I don't know, something else.
Why?
Or, yeah, versus maybe a bee. Now, if we think about that as being vibrations, right? What would we have to change with the slinky thing, the slinky model, to actually get a pitch change? Would we be changing how hard we push it, or how fast we move it?
Oh.
Fast. How fast? Here. Kyle, since you're handy here, will you hold over the end of that? Okay, now watch this. If we did this, oops, that's all right. All right, if we went ahead and, how about a little charades? See what I'm acting out. I'm going to do one thing. Watch this. Versus this.
That is easy.
Okay, what were my two things I was acting out? Any other ideas? I was doing, yeah, Jordan?
Oh no, you can go ahead.
Oh, I was just going to say, one time I was going slow. This time
Yeah, you were going.
I was going faster, or I was changing the frequency. And the more vibrations, what do you hear?
Higher pitch.
Higher pitch, okay? And what else did you guys notice? If you think about the distance between the waves, that's the wavelength. What was happening to the wavelength? Watch, I'll go from slow vibrations to fast and watch what's happened. Watch the distance between the compressions, okay? Now I'm going to go faster.
They get way closer.
They get way closer, which means they're
Moving faster.
shorter. So shorter wavelengths are higher pitched or higher frequency. Okay? Awesome. So I'll just show you an image of how this kind of, here's what we did. We pushed and pulled the slinky. It's kind of how we think of the particles transferring energy. Now, we go to here. These were the, I guess, the words that you kind of assign to the compression, or the dense part of the wave is the compression, and then this part, rarefaction, is the kind of that stretched out part. I think, which part were we seeing as we tracked it down the spring? Were we seeing the compression or the rarefaction?
Compression.
Yeah, I guess we were seeing both, but what was easier to notice?
The compression.
Yeah, the compression. Okay, so if you take a look at this, it just shows how we can measure the wavelength of the slinky, or if this was air, the sound. And it's the distance between the two compressed parts or the distance between the two stretched out parts. Does that word kind of fit? I mean, it's a wave and it's the length of the wave. Yeah. So, I guess one of the things that I kind of wanted to squeeze in just a little talk before we change our last drawings of our instrument is we talk about a little bit of difference between the wave and how it sounds, but what happens when it gets to the ear? I know people had some different readings about what's happening in your ear or once that sound hits your ear. Anybody want to kind of summarize for us? Yeah?
The pineal catches the sound wave and then travels through your ear canal, then passes through the eardrum, and then the bones amplify the vibration and to move a liquid in the cochlea.
Yeah, does anybody know how to pronounce that for sure? It's a weird word, right? I think it's, I've heard people say cochlea or cochlea, but I think that's close.
Okay, and then it transforms the vibration to something that our brain can understand.
Okay, yeah, so outer ear here, the thing that we see, ear canal, perfect, and this hits the drum, just like a sensitive drum back there, vibrates, moving into here. And the tiny bones, I guess, we're better seeing in here, right? This little series of bones, and then moving off to the part that makes sense of that signal. So, a lot of little things you can kind of see how whenever I rang that fork, some people were really sensitive to it, right? Did anybody feel like that really kind of like there was a lot of force on their ear when they heard the little one?
Yeah.
Yeah, it's sometimes it's kind of painful because of how sensitive this is. So, I guess what I want to move us towards now is, I think I had anything else. Oh yeah, I did have this picture here, and I wanted to ask you one thing if you noticed this. We kind of talked about this with the slinky. This is showing the amplitude difference in a wave. Amplitude can, in a sense, be thinking about how close together we've got that, or how compacted and how far apart things are in these types of waves. So if we look at this, is the wavelength the same or different between these two things? Think back to what wavelength was, the distance between the waves. Is it the same or different? What do you think? The wavelength, or the distance between each wave, is it the same or different between this one and this one?
A little different.
How about this? Look at where the compacted part is. Look at where the rarefaction is, compaction. And now if you take the spacing of them, the wavelength is actually the same, but what's different?
How compact
it is.
Yeah, how compact or how spread out it is. And that gives us an indication of how much energy is there, or we hear that in volume. Because did you see how that compaction changed whenever Luis and I really pushed it hard? It got really compact and really dense, like you said. Okay, let's see. I'm looking at the time, you guys, and what I'm thinking is, depending on, I guess, no matter where you're at in this process, I want to go over some of these big ideas with you as a class, okay? So I want to show you this. I'm going to turn, just for a second, I'm going to turn the lights down. This is just a model of how we think of sound traveling through air particles. See how the fork is kind of in its out position, like flexing out, and then it's flexing in? See how it creates that wave or that disruption of the air particles as it energy moves away from the fork and through the air? Okay, that's like whenever we were moving the slinky back and forth. So, are you guys with me with the high pitch one vibrating fast and the low pitch one vibrating slow? Okay, so let's see about this.
Oh, I got you.
In this picture, is there any problem, do you think, with what's going on there with the sound wave traveling away from the fork? Is that really accurate? No, this is actually computer generated. Do you think that this is accurate? Notice how it's kind of traveling in one direction like a slinky?
No. I think it's okay.
Is there anything that you could change to make this model maybe better?
So the smaller the object, the louder it is, and the bigger object, the so
Well, I think that that's been true sort of with what we've seen. We've seen large drums have low sound and small drums have high pitch. And that's like the I guess how high or low, not really how loud or soft. Tell me this, you guys. If I have this tuning fork and this is the low one, and I do this, can you hear it?
Nope.
Can you hear it? Okay, let me do this one then. Can you hear it? Can you hear it? Can you hear it, Jacob? Can you hear it? I can hear it over top of it too.
It goes everywhere.
I can hear it underneath it. Okay, so look at this. Is there any way that this could be made to be more accurate?
Sphere, a circle.
Make it go all the way around it? That's kind of what I was thinking. Now, if you guys had, if you had to demonstrate how sound really acts with slinkies, what would you do? Would you use one slinky? What'd you say? A ball slinky, one that goes in all directions, right? Yeah, I wish we had one of those. Or I could connect like 6 or 7 slinkies to a round object and then hit that object and have the energy move away from that. Yeah, I'm glad you guys agree with that, because I think that'd be more accurate.
So the vibrations create the sound, right?
The vibration creates the sound.
Yeah, so what if the bigger tuning fork had, since it's bigger, it gets less vibration, so it will make a lower sound.
It has, say that again, the bigger one has what?
Less vibration, so it will create a lower sound, higher, and the smaller one, you get more vibrations to create a higher sound.
Exactly, okay?
Covered dots.
Non-compressed dots?
Probably.
Changes what you drew.
Well, we would change some of that. We would write more of what it is.
We added this today with that. Okay, it's just
Sure,
to
it's
see
something
how you
for
guys are progressing and how you're thinking about things.
Like we could change
And
that
could
and
be a
write that.
description of
What, Dave? Yeah.
this
That one.
writing or drawing.
'Cause that's how you catch the sound waves.
Are there things on
Wait,
here, you
no,
guys, that you wanted to take a few of these and put them on and then say, well, we think about this a little differently now?
Probably change that into saying more of how sound is here.
Okay, so I'm seeing, and I remember this from our discussion before, you were just representing sound here. Okay, so would you want to draw a little bit about how you're thinking this looks like instead of this, it looks like this now? And then you could use this to write a little bit about you're thinking this now. That work?
Yeah, I guess.
I mean, now, when you guys think about this in your head, what sound's looking like traveling through the air? What are you envisioning now? Is it still, does it still fit it?
Kind of.
In what ways?
Well, the music is flowing through the air, vibrations. But
Okay.
You could draw like pictures of vibrating.
What's vibrating?
The sound vibrating through the air.
Is the sound itself something, or is there vibrating of something else making sound? That, the second thing I said? So let's do this. When the piano makes its sound, what's it vibrating against? You know, when the little hammer hits the string, what's next to the string that gets vibrated?
Darn it.
Or how about this? Let's go back to the tuning fork. I strike the tuning fork. What's the tuning fork hitting?
The table.
First, it hits the table. Now it's vibrating and it's hitting what?
The air.
Yeah, it's surrounded by air, right? So when the air is vibrating, the air can carry that energy away from the tuning fork in the form of a
Sound wave.
yeah. Now what's that sound wave look like? You have the reading. Think about the slinky. Think about those last slides.
Okay.
Does the sound wave look like this?
Kinda.
Kinda.
Not exactly.
How not? How is it kind of though?
Because the sound is in the air. And we could just like draw a line here, a line there, and then sound notes going through it.
Why don't you do this? You can look back here. This has the same diagram. This is what's happening with the fork. You can kind of think of that as like the string. But then a little expanded view is shown here.
Yeah, that's what I just said, except I said sound notes.
Oh, okay. Well then I'm gonna leave you guys, and then you guys can make changes of what you think is looking different, how it's looking. You add some slide.
So, you want me to like...
I think the yellow
Just dots. Really close.
Just dots. Yeah, we'll just do it here, a little section. You don't have to do the whole thing. Just like kind of describing air particles.
So like
And
compacted, right?
yep. Like all together and then kind of loose and then together. Just do like a constant one. Where are you going?
We need like a marker.
I don't know.
I'm really close together. I'm sure I do.
Yeah, light blue would be fine. I want to use a big one so we can describe what's going on.
Yeah.
The big one. Oh, so right, good. Okay.
Drawing that one.
So, why don't we do this? What was this showing before?
The sound coming out.
Okay, the sound coming out. Now thinking of everything we've talked about, just in the last couple days, what do you guys envision the sound actually looking like now? Think about whenever we talk about this thing. All right.
How big are you?
Remember how this
Just like, okay.
represents air? How could you draw the air carrying sound?
I'm going like... I don't know.
Well, you were showing me what you thought the wave of sound looked like, remember? And it looked like this, you were saying. Remember what Luis said? He showed it going like this, right? The slinky was moving, but when we hear sound, what's actually moving? The sound, or is it vibrating air?
Yeah, vibrating air. The vibrating is vibrating hard enough for the music to come out.
Okay, now when we finally hear it, what are we hearing? We're hearing the vibrations against our ear. Now, is there a way that you could show more detail here as what's coming out and how the sound's traveling? Because you've got notes here. But how could you tie in what we talked about to this? And Dion, could you write a few notes about what you were saying?
Yeah.
Okay. If you promise, Teresa, to give this back, I can loan you this one.
That's about it, right? That's everything else. Pitch is what you do. And then draw an ear, like a super large ear.
Or we can do aerial. Draw like an ear bones and everything.
You want to do that?
You know how hard that'd be?
I don't. We try to find a 101.
Oh yeah, we don't even have to do it. We can put on a poster.
You want me to start on that?
Do you want to?
Not really. But, you know, it's something we learned.
So is that your shirt?
Is that what's traveling? Well, what did we learn about here? Remember whenever I showed you the chimney?
Level.
Is that what you're thinking of the air is looking like? Okay, so if that's what, is that at each little piece of air? Okay, hold on a second. So are you saying that you're thinking, how is there some air that you were saying was, I heard you say that there was some of it going back and forth? Okay, so are there some times where these things are closer together? Is that what you're saying? Okay, show me a drawing that shows them the way you think that they look when they're going through the air. Okay, then let's draw an extra drawing about what you think that they'll look like now. And you know, if you don't, these are the way that we write it on paper. If you want to go with just little dots to represent the air, you can do that too.
I wrote the sentence twice.
That's okay. You can just scratch out whatever you need to. This is just a work in progress.
This is what it looks like.
Okay, now will you label those with an arrow and tell me what you're thinking those are?
We're separating then and confusing.
What does that have to do? Oh, that's way. That's a spaceship. So I'm trying to draw another.
Okay, I saw that you used they. Who is they? What are they? Those are notes?
Or should I say that's?
Huh?
Or should I say that's?
Okay, you can see dots. I was just wondering because we were talking about these were notes, but then you said something about, is there notes in the air when I talk?
No.
Even if I, how about if I whistle?
Yeah.
Then there's notes in the air? Well, what's in the air now when I'm talking?
No notes.
What if I sing? Is there notes?
Yeah.
But if I just yell, what's in the air?
Nothing?
Is there still sound?
Yeah.
But what does the sound look like when I'm talking or yelling versus singing?
When you're yelling, it's just shouting
How does it look different in your mind? Close your eyes for a second. How does that look different? See, they're both sounds, right? How about this, Teresa? If I have this in your mind, how is the air moving around this?
It's getting closer,
Okay,
and then it's separating.
it's getting closer and then it's separating. So, kind of like you're talking about here.
Yeah.
So what are those when it's coming off this?
Sound?
Is it sound or air or notes?
Air.
Put air then.
Okay.
Okay.
Like this.
So I'll leave you guys to make any other changes you want. Use as much paper as you want, okay?
See, it goes like
And
this.
you can put it over through that.
It goes like this. And as the thing goes down, it goes up and it goes up like that.
Okay. Now I'm gonna ask you the same thing. What are you saying? It goes up.
When the like when you go like this, like the sound is going everywhere. Like the sound will go like a wave to the person, and like the little sound noises will go like it goes like the noise will go as a wave everywhere, and like the little pieces will like go like as the rope goes down, it will go down without going through it. Like when it goes up, and it'll travel.
Okay, now when you hear this, is the sound changing? Or is it just one sound?
One sound.
Okay, so are they going up and down like this?
No.
I'm just wondering what you're thinking.
No.
Now these look like musical notes, right?
Yeah.
Okay, now when we talked about this, what's coming, you said that there was sound coming out of here, right? What does that look like to you? I'm going to ask you the same things I asked Teresa.
I'm not really sure.
Okay. Do you remember seeing anything that helped you think about what's happening to the air next to this? Think about this. You know this one that we can see? See this one? Watch. See how they're moving? Okay.
Oh, I get it.
There's air around it, right?
Yeah.
What happens to the air that's right next to it? Do this. Watch. Put your hand close, but don't touch it. Can you feel that?
Coming out.
Okay, air is coming out at you, right?
Oh, I get it. Like what you
Can you draw on here what you're thinking it looks like? You can even draw a fork.
My favorite instrument.
Laughing for
Now, going back to this, what is that you're showing me there, coming off of this?
when it moves, like when it's shaking, it's pushing air out,
Okay, can you put,
and like that's where the sound's coming from. Like
okay, let's write that down before we move on. So, put what you were saying, you said pushing air out. Okay, stick that on here somewhere, okay? And if you want, you can put your initials on it.